Hello everyone, welcome to my channel Coding Together. My name is Vikas Oja. Today we will see another uh, algorithm, that is simple DFS in graph. So today's topic will be DFS in graph. DFS in graphs. Okay, so we are given with the adjacency list of a graph and we are given the graph here. So we have to perform the DFS traversal. So DFS traversal uses stack, implicit stack. So now we will start with the node A. So we will perform DFS of A. Also, before starting, we have to create a visited array. So for 3, 4, 5, 6, 7, that is A, B, D, E, F, G, H. So this is the visited graph. So we'll start with DFS of A. Now DFS of A, we entered A, we will mark A as visited. We'll check the adjacency list. For the adjacency list of A, we have B and D. So we will perform the DFS of B and DFS of D. So B is not visited, so we'll mark visit B as visited and D is also as visited. Now we will see the B in the adjacency list. So from the adjacency list, B has A and D. So A has already been visited. We'll check the other neighbor, that is D. D is also visited, so we will not do anything from B. We'll stop here. For the D, we'll check the adjacency list. So in the adjacency list, we have A corresponding to D. So A is visited, we'll do nothing. We'll check B. B is also visited, so we'll do nothing. So it's empty. So it's done. So now we will backtrack from here, from B, and from D also we'll backtrack and we'll reach to A and we'll get out of A. So this for loop that we have here, we started with the 0th node, that is the first node, and if the visited V is equal to false, so for A it was false and we performed DFS. Now when we get back from A, now we will see for B the other vertex. So the visited for B is 1, so we will not perform DFS. It has to be false, means that it has to be 0. Now we will check for D. So D is also false, we will not perform DFS. Again we'll check the next vertex from the graph, that is F. We'll check F. F is not visited, so if the visited is equal to false, we'll perform DFS. So again DFS of F will be performed. So for F, we'll mark the visited as 1. Now for F, we'll check the adjacency list. So in the adjacency list, we have E and G. So we'll perform DFS E and DFS G. So E is not visited, so we'll mark as 1, and G is not visited, so we'll mark as 1. Now from E, we'll check F and H. So F is already visited, so we'll not do DFS, and H is not visited, so we'll mark as 1 and do DFS for H. So DFS H. Now from H, we'll see it's E and G. So E is also visited, G is also visited, we'll not do anything for H. So we'll backtrack. We come back to DFS E. So now for G as well, if you'll see G, F and H, F is also visited, H is also visited. So from here G will also not do anything, it will end here. Now for DFS E, we'll again backtrack to F and for G we again backtrack, because for E all the things is done, so we'll backtrack, and for DFSG we also backtrack, and from F we'll get out of it. So for F we are also done. So the next node is E. We'll check whether it's visited. Yes, it's visited, means it's 1. It's the visited is equal to true. So true is equal to 1 and false is equal to 0. So if visited is equal to false, then only we will do DFS. But E is visited, will not do DFS. H is also visited, will not do DFS, will not perform this action. And if for G is also visited, will not do perform the DFS. So this is the way we will do the DFS approach. Now let's see the time and space complexity for this. So as we see, we have created our visited node. So we might be initializing each node to boolean equal to 0 or false. So for that we can take order of V. So here it's order of V. Let me order of V. And for this for loop, we are, for every node V, every vertex V, we are performing the for loop. We are doing the performing for loop. So it will be order of V. Now this DFS block, now here we are doing some constant work, so it will be order of 1. And for each U in adjacency list V, we are checking whether it's visited equal to false. Then we again doing for that child or the neighbor of V the DFS, recursive call, as we saw. Now only when the visited is equal to means false or 0, then only we will do DFS. So this for loop is approximately big O of E, and this constant we are performing for each node. So each node or each vertex will be visited with this DFS block, and for each U in adjacency V, this for loop will be executed approximately that big O of E, the total number of nodes. So if you'll see this adjacency list, so we'll have the in the adjacency list the number of edges represented in the graph. So from A to B we have one edge, A to D we have one edge, and so and so forth. From every vertex we, whatever the number of edges we have outcoming from that vertex, we have listed in the adjacency list, and we are traversing over those edges. So this for loop will be order of E, time complexity. In another way we can say that whenever we are doing DFS, so we are reaching every node and we are doing a constant amount of work, that is we are marking visited equal to 2, so it will be C into, we are doing some work in this for loop. So let's say for each node we are doing some n iterations, so it will be different for each node. So for first vertex, when we are iterating for first vertex, it will do a C constant amount of work, and it will do some n operations, plus again the same constant work for vertex 2, C into vertex 3, and so on till C into whatever the number of vertices NV. So if we take C out, it will be V into C. This constant amount of work will be done V times, because we are doing DFS for all the nodes. At least all the nodes we are doing DFS. Plus when we sum the amount of iterations in this block, this N1 plus N2 dash NV, it will be the number of edges. Whatever the number of edges we have in the graph, it will be this. So the total complexity becomes order of v plus order of v from this loop plus order of v plus e. That will approximately become to order of v plus e. Now if you'll see, for this example we have used undirected graph, so there will be the number of edges will be 2e, so the time complexity will be v plus 2e, that will again approximately big O of v plus e. So yes, this is the time complexity that we talked about. Now we have already seen the code. Once again I will iterate the code that we have initialized visited as new int v. We have initialized this visited array, and we go through each vertex of the graph in this for loop, and we do the DFS for it. So in the DFS block we mark, whenever we go inside the DFS block, we mark the visited for that vertex as true, and for the adjacency list we take out the neighbors for each vertex and perform the DFS if it's not visited. If the visited equal to false, then only we'll do the DFS as we saw. Okay, so there is one more thing that we can talk about, that we took the adjacency list here. We can take the adjacency matrix also. So the only difference between the adjacency list and matrix is that the adjacency matrix is a 2D array. So this, whenever we are taking the elements, then in this for each loop, the u in adjacency of v, so in order to take from the adjacency matrix, so suppose adjacency matrix will be like 1 2 3 4. I'm taking one example here. So for let's say for this example, a b d e f g h, a b d e f g h. So the adjacency matrix will be, if there is a edge between a to a, so there is no edge between a to a, means there is no edge like this, so we will mark it as 0. There is a edge between a and b, so we'll make it 1. If there is edge between a and d, so we make it 1, so and so and so forth. So 1 represents there is a edge and 0 represents no edge. So in this way, for here there was, in the adjacency list there was only those elements or those nodes which were directly connected to the A, but for in the adjacency matrix, for each node we have all the other vertices we have to scan. For each node we have to scan all the other vertices or all the columns of the matrix to figure out like which with which the A is connected with, or is there any edge between A and B, A and D, and so on and so forth. So we have to find the edges between the corresponding nodes. We have to scan all the elements. So for this, each loop will go for v times, every time v. So as we saw that the time complexity was v plus e, now for this we will go every time v into v, that is v plus v dot v, and the time complexity will be equal to v square, because we will not perform this for loop big O of e. It will be performed for adjacency matrix equal to order of v square, because for each node we have to scan the complete columns in the adjacency matrix to find the corresponding edges, and for that edges, so that we will perform DFS on. So in that way the complexity will be v square. So the adjacency matrix will change the complexity of the graph to v plus e to v square. Now we will talk about the space complexity. So we are using a visited array that will have order of n, order of v, the number of vertices, plus we are maintaining the adjacency list that will be order of v plus e, because there is all the vertex, all the keys as a vertex inside the list, and these are the other vertex which represents e. So it will be o plus e plus the auxiliary or the implicit stack with this DFS approach can have, like, the DFS can go from A to B, then B is connected to D is connected to F to connected to E, H, G. So the worst case that the implicit stack can contain all the elements, or the vertex, so it will be order of V. So the space complexity will also be V plus E. Okay, so hope you liked the video. For the example of this DFS, I will present one more video, that is course schedule, where we will see the example for DFS actual application in an lead code problem. So stay tuned in that video. Till then, bye.